Welcome to the post-event celebration of Crazy Web Game Jam 2024. Our very first jam has been an incredible journey, and it's all thanks to you. This year's theme, Everything is a Remix, inspired the participants to blend genres, mechanics, and ideas from all over. The results were nothing short of spectacular. Out of hundreds of incredible submissions, these outstanding games were chosen for our incubation program. These teams have shown exceptional creativity, innovation, and dedication. The Crazy Web Game Jam brought together over 2,000 developers from across the world, from seasoned veterans to first-time jammers. Every participant showcased the incredible power of creativity. We had 317 games submitted, a community brought together. We want to extend our deepest gratitude to our sponsors and partners, including Indie Hero, Crazy Games, Unity, and Photon for making this jam possible. We also want to thank all the mentors and judges who helped us during the jam. But above all, we want to thank you, the jammers. Without your incredible talent and hard work, this jam would not have been possible. The Crazy Web Game Jam 2024 was just the beginning. Stay tuned for more exciting events in the future. Until then, keep creating, keep innovating, and see you next time.
Hello, everybody. Good evening, good morning, depending where you are in the world. My name is Rafael Morgan. I am the VP of Marketing and Partnership, and together with me, I have Rabia, the Partnership Manager at Crazy Games. We're super excited to be here and kick off the incubation with the first masterclass, which will be about web optimization. As the video show, we had a lot of participation on this game jam. We're very happy about that. Over 2,000 people joined. And over 300 submissions, which means that the 10 incubated projects like you guys who are here today are the ones that, sparked up the most into the Crazy Games team. So we're very excited. I know that some of you or all of you already have conversations with your manager, and things are going pretty smooth as far as I heard. So we're very, very excited, and that's why we're organizing those masterclass as well. But before I introduce our host for today, I just want to explain a little bit about the format. So it will be a presentation, 40 minutes, and then followed by a QA. So if you have your questions, please post them as comment on YouTube. We'll be reading them. We have a very nice prompt that we can push them here. So we can, I'll be reading that, and our guests will be answering those. Okay, so I think we're ready to start. We have a very special guest today, somebody that is changing the web gaming industry. So I'm very proud to host him today. Is Josh Loveridge is the director of Stratton Studios, and he's the creative mastermind behind Project Prismatic, which is an upcoming game on Crazy Games, and it's a really I think it's mind-blowing what they are doing in terms of WebGPU and optimization, and I could not think of a better person to talk about this topic. So, Josh, say hello to everyone, and feel free to take over the stage.
Hi guys, great to see you all. Hope everyone is doing well. And yeah, excited to chat to you about what we're doing and hopefully share some of the learnings that we have made during the creation of Project Prismatic. So just before I dive into Project Prismatic, I'll just run through kind of how we got to where we are now. Stratton founded it, a long time ago now. Essentially, we've primarily acted as a co-development studio for a very long time, and worked along really cool partners like Unity and a bunch of other guys. More recently, we've started to make our own games, including Project Prismatic, and as well as PGA Tour Rise. And really, we're just trying to make best-in-class games across the board. And primarily, we've found ourselves operating in the mobile space, and more recently, the web space, focusing specifically on the WebGPU stack. So for some of you guys, if you don't know what WebGPU is, I think it'd be just helpful if I set the context for anyone that's not familiar with it. WebGPU is essentially a kind of like an evolution of the WebGL stack. Pretty much it's a graphics API that just brings the ability to utilize like the GPU in your device in when utilizing the browser. So it's been worked on for a very long time by a lot of really cool people, and yeah, it's nearly ready now. And the standards got pretty well adopted across most of the browsers. So now it's time, and it's getting close to production use. So it's been something that we've been playing with for a long time, and now Unity 6 supports it, which is awesome. Yeah, so it's really cool. So I've talked about what WebGPU is a little bit, just to set context for anyone that wasn't familiar with it before. Let's just cover real quickly what Prismatic is for those who haven't seen it before. So Project Prismatic is pretty much our like project that we really wanted to make to showcase that you can build a console quality first person shooter in the browser. And we wanted to not sacrifice on quality or anything like that. So we were targeting a 16 millisecond frame time on mid-level gaming hardware to keep the game accessible. And really wanted to push the boundaries of what you could do with Unity 6 and the WebGPU graphics API essentially. And we've been working on that for the last while. We one of the core design pillars is we didn't want to sacrifice performance or increase the packet size to make it 20 minutes to load. Needed to be quick, snappy to get in, and run pretty much anywhere, which has been awesome. So before I dive into anything else, I'm going to show you a sneak peek of where Project Prismatic is at today. Not many people have seen this, so yeah, it's going to be. I think you guys are going to like it, and I'll talk through a little bit as we go.
Solid station. Estimated docking in T-minus 30 seconds.
So as you can see here, we're setting this kind of, train scene. We've got a lot of things going on. We've got some compute shaders in the tunnel area. We've got we've got GPU skinned animations.
Please disembark safely and move quickly to the hangar base.
And then as we move into the airlock, we can see we've got VFX graph coming in, playing some nice steamy particles, which wasn't traditionally possible with the WebGL graphics API.
Pressure equalization in progress.
So as you can see, it's quite a live world, lots happening, lots of characters to meet. Got nice little robots that we can interact with. And this is recorded from the new version of Chrome, which is great. And you can see there's a frame counter up the top left, so we're sitting around 60.
Docking bay 47 is currently experiencing power fluctuations.
And the player essentially is going on this journey of they've just arrived in the space station. They are kind of, going about their day-to-day tasks, and then things take, a little bit of a twist.
Please stand clear of the outer
which is nice. And this is all essentially as the game's been loaded, and this has been streamed in from our asset bundles and addressables. So the user doesn't have to download everything at once. It's kind of as each area is accessed. So you can see we've got some hazardous materials. We've got some volumetrics in there too, which is nice also. And all real-time lighting and GI.
Power failure. Please trigger breaker.
Which is great. We've also got cutscenes, so fully animated cutscenes as well that are coming in, and kind of progress across. And this is all built to, and we've got some indirect rendering going on there in the tubes as well to kind of offload that also. So as you can see, we were kind of really starting to utilize a lot of the stuff that wasn't traditionally available, which we're going to talk about in a minute in the WebGPL graphics API, which is really cool. So really pushing the boundaries there, because that's what makes a game really high fidelity, is those small nuances. So as you can see, the lighting's vastly changed now, and you can see the GI is just completely different to what it was, which is great. And then the players, finally progress through. They've got their turning back on the power. Now they're ready to launch into space, which is where we're gonna, which where the video finishes up essentially. So that's kind of like the first preamble of like when the player drops into the game. which is really nice. And we've been working on that for a little bit. So essentially, here's a few more screen grab dumps essentially from the game. So you can see we've got our vast open plains, which some of you guys might have seen at Unite, which is really cool. We also have full space battles and space scenes, which is also quite dynamic, and so you can kind of see the vastness of what the game actually entails. So why do we use Unity 6 for the whole web runtime as a whole compared to the older Unity versions and WebGPU specifically? So there's a number of reasons. It's multi-threading, which on the C++ side, which wasn't traditionally available, which is really cool. C# multi-threading isn't available right now, due to essentially the garbage collection and how WebAssembly handles it. But I know that's being looked at and evaluated. There's also some other kind of low-level improvements there to enable SIMD, which is really cool also. On the graphical side, and really where this helps us get that high fidelity that we're all looking for is, now we can take part and use compute shaders, which weren't traditionally available. We can also do GPU skinning, which is really cool. So we can actually have all these animated characters on screen, and we can again use compute shaders for a lot of particles, and we can also use 4+ rendering, which essentially removes the traditional per object light limit. Again, super important for all those dynamic lights that we were seeing in the scene, and then VFX graph on that side. One of the bigger improvements that really has helped a lot in Project Prismatic as well is increasing the cap for the WASM memory limit, which was traditionally 2 GB, and now it's up to 4, which is, again, awesome. Really cool. Allows us to pull in more larger assets, allows us to stream things, as we load in the addressables in the background. It just helps on that side and to keep us going. So now I want to talk about each individual part of how we are using Unity systems to actually, kind of make Project Prismatic come to life. So during the game, as you noticed, we were going through those various different sections. Each of those areas are split into asset bundles that we can pull. And we like to generally keep those asset bundles under 5 MB each. So that's baked in. That's including your textures, models, and audio. And we want those small asset bundles that are, as part of the addressable system and are pulled in from UGS. So that enables us to only load what the player needs when they need it. As soon as it's done, we just offload it, get rid of it. And that links in with the node occlusion culling framework, which I'll talk about later. But we kind of think of these as play like sandboxes essentially. So we've say might have 10, 15 micro sandboxes within a level, and that's how we're able to get all these things in, because we're just constantly loading them in and getting rid of them, and that really helps on that side. It also means that we're able to get that really quick boot time, which is super important, to make sure that people are not sitting there on the screen, and also makes the game super accessible. It also helps with the keeping the draw calls low actually as well, because we only have so much content we can put on screen at one time, and we like to use a lot of materials and shaders to actually add variety, decals, all that stuff, but not necessarily bloat out our texture limit or whatever it be, because textures are one of the biggest ways that will actually affect you. And that's a great great segue. Textures are the biggest enemy when it comes to your project size becoming bloated when you compile it for the web. It's gonna get you every time. And how we've overcome that is we've a lot of particles, a lot of various different systems going on there, a lot of decals. So we've actually started to texture cram, in that we're utilizing the full channels, like the RGB and A channel of textures, to pack all our mats. So pretty much we have texture atlases that are utilized on the RGB and A channel. So really we can fit 4 mats into one image, and multiplied by however many various different mats are in the array. So theoretically we could have 60 or 70 different mats in one image. Yeah, so it's going to be it helps really push that down, to make sure that we're only loading in the images that we need, and all of that stuff that we can push, we are pushing and making it, you know, nice and tight. The other thing we do is we procedurally generate any textures where we can. So we can see on the screen to the right here, we've got these various different rocks. They're not using any texture. We've actually just overlaid some noise from those mats in a shader graph in Unity to be able to get that nice kind of, you know, rock color. And then we've built like an edgeware shader there, which, you know, it runs quite nicely and means we don't have to have, you know, textures for stuff like that, which is super important. This, I can't hammer down on this enough. You really need to atlas everything and just really be very intentional with what you are actually uploading into the game. It'll also make your bundles more bloated if you do it incorrectly. Crunch compression is also something that you can use if you are struggling for that file size. Although, you know, that doesn't, that'll just uncompress when it actually is at runtime. So, you know, it just kind of helps you get that initial packet size lower again. But it does have performance implications on that side. So multi-threading. We've built our own interop library to essentially work with web workers, which is a API on the website, so essentially, so we can push some computation to those threads so we don't need to run them on the main thread in Unity. A great example of what we're using that for is the asteroid framework we built, which you can see on the right. This operates in a callback fashion. So after we send a request, milliseconds later, we get the response back. We use that to calculate the positions of where the asteroids are, how they're moving, how they're rotating. And we also use that for boids. We use a lot of boids in the game. For anyone who doesn't know what boids are, it's essentially like how you simulate swarming behavior. So we use that for spaceships, actually. So they can do like attack patterns and stuff like that. As they go on like attack runs and all that jazz, we can actually push a lot of that computation, the heavy computation at least, onto the web worker, which is all using essentially C++ multi-threading. So it's worked quite well for us. We've built this plugin to really, you know, utilize it for what we need, and it can pretty easily be done if you're familiar with kind of, you know, the web worker API and all that stuff, and building interop layers for Unity. So this has probably given us, I would say, 30 to 40% improvement in performance across the board, which has been really, really pivotal for Prismatic, especially all of that heavier computation. So really all we want to run on the main thread is the main character. Anything else we're trying to push as much as possible. Anything that doesn't need to be there exactly real time, we're just pushing, as much as we can at least. And then let's move into one of the other big things we do, which is matte paintings. And matte paintings are a very old film technique, actually. I'm pretty sure it was first used in Peter Pan for the waterfall scene in the background. It's actually just, all it means is pretty much you can actually use flat images in a billboard fashion with like a, you know, a slight fake depth texture there to pretty much fake geometry. You know, so as you can see in this scene, it's like a hangar scene. You can see there's little characters kind of, you know, standing around the hangar, stuff like that. Instead of having 40, 50 skinned meshes on screen at one time, we'll probably only have 5 or 6 skin meshes, and the rest of them are actually just flat images, just rotating billboarding with the player as it goes. And as long as you put in 1 or 2 animated guys in there, people actually don't notice, which is really funny. But it's an old technique, works really well. It just enabled us to, again, keep those draw calls lower, as low as we can, because we don't want to overburden the GPU, or we want to keep those precious, you know, compute cycles for whether it be VFX graph or compute shaders and anything we're trying to do on that side. But even though I will say with this, like, you don't. You can actually, you know, with the new WebGPU stuff, you can actually save a lot of performance on the GPU skin inside, and you can have multiple meshes on screen if you want, compared to traditional WebGL, which you can only have a couple and it would kill your performance. But this is an extra optimization on top of that. And you can do this for multiple things as well too. You can do this for big, large vistas in the background. You could do it for planets. You could do it for whatever you need. If the player comes up really close to it, I wouldn't recommend it. It won't work as well. But for any of those background scenery items, it's a great fit. So now we get into the LOD and occlusion culling framework that we have. And I want to spend a little bit of time on this because this is a important one. So we aren't using traditional Unity's Umbra culling or whatever it's called. We have built our own kind of occlusion culling framework that we pre-bake at create time. So essentially what we do is, and how it works is, we divide the world into spatial node clusters in BVH hierarchies, essentially. Each of them that represent a region or a group of objects. Essentially, it's a bounding box in Unity we define. We say, right, this is our, this is our hexagonal, playpen, essentially, for this area in the game. And we make those as small as possible. At the designer level, we have breakpoints. So as you noticed in the trailer back there, or the alpha video, you could see that there was turns every couple seconds. There was doors. Those are all intentional breakpoints for the node cluster culling system, essentially. So each of those is actually an area that's only been rendered, and the area after that doesn't get rendered until it's needed specifically. So that means that we're actually only trying to push on average the maximum 1,500 draw calls on screen at one time, probably from a try count perspective, like under 900K. So we're really trying to hit for those numbers. We don't hit it on all scenes. So extra beefy than others, but that's what we aim for. So as we pre-bake these areas, essentially what we did then was we built this like a manager script, pretty much, that each frame it checks how big or how much the cluster is in view. Once it hits past the threshold, using the depth buffer data, it then essentially will dynamically enable parts of that cluster as needed and to come on screen. But the second a cluster's completely outside of the view box, or it's outside the and it's blocked away, we can then use that data as well to help inform our addressable system, so we can kick data off and get rid of it. That's another big strategy that we've utilized. Is we're just literally getting rid of as much data as we can when we can, because that just it just makes things so much easier on that side. Super important, this one. This works in tandem as well with the other optimizations that we've done, like general LODs. For anyone that's not familiar with LODs, just level of details, just essentially loads lower resolution models as you go, and kind of dynamically scales them across the board. And then GPU skinning, of course, across the board. That's super important as well. So, great segue. VFX graph, GPU skinning, and then on the computator side. I also want to talk about a few techniques that we've utilized as well, like parallax mapping, to really achieve some of those high-level details in the mesh topology that we've got without actually adding extra verts onto the meshes. Project Prismatic fundamentally is a living, breathing world. We are not willing to sacrifice on that design intent at all. We can't. So whatever we needed to do to get there technically, we were willing to do. So we found this really cool mix, and this is super evident in the forest on Planet Arcus that some of you seen the Unite presentation. That world is living and breathing. Even the plants are skinned. They've got bones running up through them, or they're procedurally animated. Everything moves. Everything has life to it. And to do that, we weren't going to be able to use just traditional CPU skin. It just wasn't going to work. Too much of a performance bottleneck. So with Unity 6 and the new WebGPU graphics API, you can use GPU skin. So we're pushing 20, 30 different skin meshes to that to the GPU at any given time. in various different forms, and we're animating them from there. We also will procedurally animate via just general scripts when we can, or using like a tweening library, if that will work for that item. But oftentimes for stuff like, say, the trees, or say the the big alien plant monster, sorry, and they kind of move, sway, and look at the player as they're going, and they go from there. And we also use blend shapes a lot to dynamically change different mesh topology as we go. But again, it's all getting pushed to the GPU. Super, super important that you make use of that. The other element that I also find really, really important is the parallax mapping. So for anyone that's not familiar with parallax mapping, it's used in a bunch of games, some really cool ones like Genshin Impact, or any game really uses, to be honest with you. On the right, you can see on the rock textures, we've got these really fine-grained details in there. That's a mix of your traditional, diffuse map, normal map, spec map, occlusion map, and then we've got that baked into a parallax occlusion mapping shader. Pretty much what that does is it simulates depth where there's depth. Which is great for kind of those areas that have, kind of crevices or anything like that. It's really good for that side of things. It just makes it super super easy to add that detail there without actually really needing to add that into the mesh topology. Because if you did that, it'd be super heavy and you just wouldn't be able to have it on screen. Like, I think that rock there on the right, they've got the screenshot of, it's like only, a couple hundred tries at max. And it's mostly just flat planes, but we've kind of faked a lot of detail in there, which looks great. And then once you've your real-time GI in it, the magic happens and you're good to go. So from there, we use VFX Graph a lot. For anyone that's not familiar with VFX Graph, it's Unity's kind of next level particle framework, pretty much, enables you to use the GPU a lot better than what was Shuriken or Unity particles, and allows you to do these mass simulations. And all the fog in the game is pushed straight to VFX Graph. We have a big, kind of volumetric VFX Graph going on that enables us to do that in the world, which is really nice. And we also have like dust particles coming in constantly. Any of the muzzle flashes from the guns also are all on VFX Graph. And then in that space scene, the whole space simulation is actually being ran. A lot of it is being ran on the VFX Graph side. So there, that's everything from like comets to starfields to all that good stuff. And then in space, kind of space-based scene that you looked at, you could see there was a lot of steam particles, a lot of sparks, all that stuff, and all those have collision and all this stuff, which is all being ran in VFX Graph. So super, super good framework to get to know. And you just install it in Unity, and then you're essentially off to the races with it. Which is it's just really good to get to know. And then let's talk about results and how and where all of these combined into one has got us. So we're achieving our 60 millisecond frame time, as you can see from the video. And the game's still in development, of course, but we're getting pretty, close to finding the sweet spot on that side. On mid-level hardware, with VSync on, you're getting like 60 FPS or 60 millisecond frame times, which is great. It works really well, and it's accessible across the board. So it means low-level hardware probably going to be around the 30, which is fine. But a mid-tier up is going to be at that 60. It keeps gameplay fluidity, and it's solid 60. It's not choppy, which is good. And also it just kind of keeps that design intent behind, kind of not being willing to settle and provide that console level experience. So that's on the frame times, super important. And for anyone that doesn't know, you should always measure your frames per second and frame time rather than FPS. It's just, it's a better way of doing it, and more consistent. Then build size and download packet size. So our initial payload, we've got down to as low as 29.75 megabytes. We are still actively building this system, so it's constantly changing, evolving. Well, essentially, that is just the initial, essentially, main menu, couple meshes and materials for the initial kind of addressable that's loaded in, and that's pretty much it. The rest of it is all streamed in as we go, and we just load the addressable as you go. And because they're in those 5 megabyte packet sizes, so to speak, or around that, it just means that it's much simpler to stream those things in as we need. And then we generally like the memory limit to sit around that. Right now we're sitting mostly around the 2.7, so we haven't even got up to 4 yet, which is really cool. But we're doing that because we want to make it. We're not going to use memory for the sake of using memory. Doesn't make sense. So that initial payload size gets us that's the initial thing people download, and then there's an addressable that's loaded in the background as the players, in the loading screen, listening to the preamble, watching the cutscene, all that stuff. And we're using dynamic breakpoints, as we're calling them, where we can actually load in the addressable, even queue up 2 or 3 addressables ahead. So the players constantly, even if someone was to blaze through the content, they're going to be loaded in and ready to go before the player actually hits them. That's super important. We also have this cool system where it's like where it's also super cool, because what we can do is we are able to dynamically slow down the player if an addressable isn't loaded. What do I mean by that? We have like this system where we can actually start to pretty much add more obstacles into the game, into the different bundles, so to speak, that are hidden normally if the player is actually speeding through the game quite aggressively. Great example is in the forest scene, we can add in a bunch of raptors pretty much to attack the player, which will distract them for a minute, and then pretty much they go from there, and then they're it gives us that extra time to load in the addressable. So we can dynamically do that, and we can keep spawning them in until it's loaded, so the player doesn't actually really notice that it's because something isn't loaded yet. So that's why that's happening. We also do that with cutscenes. So those little mini cutscenes that you're seeing, they're all just to slow the player right down, and to essentially give them both that break from a gameplay and fluidity perspective and synergy perspective, all the way down to essentially the gameplay side of things. So that's build size, initial packet, pretty low, and we're going to try keep getting it lower. Might go a little bigger, but we're this is a constant battle that we're fighting, and we don't want big packet sizes. It kind of goes against the ethos of what we're trying to do with the web game side of things. Now let's get to boot time. This is an interesting one. So the 1.87 second metric is a vanity metric. I always say that, and that is with optimal server conditions, very close by, all that jazz. But it shows what's possible. And realistically, anything under a couple seconds is going to have a great experience for the player. You need this boot time to be lower. Generally, I always say, you want a scene, some sort of preamble scene, and don't just jump them into gameplay. You should have a menu going or other stuff like that to be able to essentially, make sure that the player is, not just jumping into things straight away, because that's going to take Unity longer to spin up. Instead, if it's just spinning up a flat image that looks nice and has maybe some text for the player or something like that, then generally you are going to actually, be in a much better position to be able to, present stuff to the player on that side. One other thing that's very important for this too is to make sure that you essentially aren't in your loading scene or your start scene, that you aren't actually doing too much heavy on the computation side. So you would great example, if you have an object pooling framework in your game, maybe don't place that in the loading screen scene, because then, especially if that's loaded on start, or wait for initialization or first contextual paint before it actually does that. Because if you have that and on awake on a start, fill my object pool, and you've got 50,000 objects in there, then it's going to slow down that it's going to cause a big GC spike at the origin of the game, and then you're going to have issues. So really just keep in mind, make that starting scene as small as possible. Also, one thing to note is on Unity with the new web runtime template for like the presentation side of things, you can actually make a nice little animated loading screen in React, and you can do whatever you want there. It's just really a HTML page, or you can even embed it in a React page too. So you can actually put like various different elements to distract the player there, have a nice little loading screen. Even if things are going from there, you can just kind of keep customizing from that side. So really do that. I see a lot of web games where that isn't a thing. It's like, it's just the base Unity template. It doesn't have to be like that. It can be really cool, and it can be customized, and you can also inform or load in normal JavaScript there as well. It's really important on that side. If you take these techniques into mind, you're going to make sure your game's super accessible on that front, which is awesome. And one thing I will note as well, Project Prismatic runs on mobile too. It does. It's not meant to be played on mobile, and it will be probably a really bad experience because it's meant to be a console shooter game, so controls aren't optimized. But that is one of our litmus tests internally too, is can we run it on mobile? So we launch it on mobile, see what it runs, see what the frame rate's like. On most high-end devices, we're getting on new iPhone, we're getting 60 frames a second, which is great. But again, not really intended for it. The only other one thing I would say on this front that I think is important, and I didn't put it in the slide, but is that you want to make sure that, and one thing that we've just added in the last 2 weeks, which is really cool, is make use of Unity's new script culling API. It's actually really cool. And what you can do is you can actually have, traditionally in Unity, you can call objects that aren't in your camera's frustum. So if something's not in the camera's view, you say, don't render it, don't turn it on. You can actually do that with scripts now, which is really cool. It's been out for a while. Not many people know about it. And, you can, push on that side to get some more of those cycles. We use this a lot for any of the spaceships that are on scene. So when they go out of view, they actually stop simulating. So they're not actually simulating in the background. The player doesn't know it because they don't see it. And then we just actually, as they're coming back into the player's view within like a 20-degree angle, we actually restart that simulation and maybe accelerate them forward like 20 units or something, so the player thinks, oh, they moved, but they actually didn't. That's another really cool one that has saved us a lot of performance. But other than that, we're gonna jump into some questions. I want to make sure you guys can get anything answered you guys have. I think you're on mute, Raf.
I'm talking to myself. So I was just saying, amazing, really crazy what can be done in the browser these days. Obviously, very much in the forefront of the development into the WebGPU. I also I think that, but for the people that are watching right now or will watch this later, I think there's a lot of tips that you can apply this on your project, and I think that's the intent about these talks as well. But yeah, super cool. We have some quick QA time right now, and we have quite a few questions that were dropped during your talk. So I will just read it, and you're free to talk. And if people would still want to comment, you can also use the comment section as well. So JJ Lee asked, how many hours have you spent on Project Prismatic development so far?
I'd hate to think a lot. I'd say, actually, I've never thought about this, but let me just run. I'll tell you now. 32. So we're probably spent, Project Prismatic's been in development for nearly 9 months. That's probably say 2. I'd say about 6,000-7,000 hours total across the team. So it's been a while.
Well, you can see it, right? That's
let me set context where that is now. We were probably 6 levels in the game have been made today. So the first one's launching in Q1, so we're probably going to launch that early January or early February. Sorry, it's going to come out the first kind of like level or whatever, and we're launching in an episodic fashion. But yeah, it was about 6 levels done with about that time frame. I would say from a technology perspective, we spent about 4,000 hours just building all the systems that we needed and to get things done.
Awesome.
Which is nice.
Yeah, well, can't wait to play. And you're gonna be able to play on Crazy Games. I'm very, very happy about that one.
Yeah.
And Ahmed is asking, while developing 2D games for the web, it is okay to use 3D physics engines in Unity. I ask this because I feel the 2D physics system might not be stable enough for real-time physics interactions.
100%. Yeah. So, I always say use with intent when it comes to this sort of stuff. There's no reason why you can't use the 3D physics side of thing for a 2D game. You're just removing a plane of motion there. And from my experience, the 2D physics side of things is pretty stable. And the only time you can get some funky behavior is if you're using like spring joints or anything like that, where you might have to do some custom implementation to get it running correctly. But other than that, you can use really whatever you want. I have seen, in some other projects that we've done on the web side of things, we've just ripped out base Unity physics and we're using our own kind of base implementation and using, one of the other off-the-shelf physics engine side of things. Or you can just go, and build your own deterministic physics frameworks. One thing I will say for multiplayer games that you're doing in the web, you've got to be really careful, because you're probably going to have to make your own deterministic like rollback solution, and which is slightly finicky when making that for a web game. It's actually, and so this hasn't been announced to date. I actually realized I've never told anyone about this. So Project Prismatic isn't just a single player game.
Oh.
It's there's 2 versions of Project Prismatic. There's a multiplayer version too. That's been in development by a separate sub team within Stratton for the last 4 months. And that is focused, because coming out of Unite, everyone was like, Josh, looks great, awesome. But they're like, that's never going to work for a multiplayer game. That's never going to scale. It's like, okay. So we've been working on that. So when we were building that, bringing it back to the physics side of things, you probably will have to, if you're doing any multiplayer stuff, you will have to do some sort of deterministic rollback solution, using depending what netcode stack you're using. Photon Quantum's great, Unity netcode's great too. It really depends what you want to use. I think what we're using for it is we're either using Fishnet or Mirror. I'd have to check, but it's heavily modified to essentially support our own rollback system. Because again, it comes back to that thing. In the web side of things, we're trying to push as much as we can to the worker threads and using that interrupt library we have. So, we're trying to optimize there as much as possible. But yeah, so hopefully that answers the question on that side.
Awesome. Yeah. We have Paulo asking, how are you approaching the creation of game interfaces? Would you consider UI toolkits the optimal choice for web games?
So this is a funny and it's quite a timely question. So there's actually, we've gone through 3 iterations. So we started out using base Unity UI in GUI, and just going from there. From there, we actually switched over to UI Toolkit, because we were like, hey, this is closer to web tech. It's getting a lot of improvements. It's in a good spot right now and super scalable. So we did that. And more recently, probably the last month, we've actually ripped that out again. And we put in a React UI framework. So we're using React as our front end essentially in the game. A few reasons why we do that. We have a lot of strong web developers on our team. So they have strong web development background. And so I was kind of having a conversation with them. I was like, guys, I want fully animated UIs that are reactive, that we can do whatever we want. And it was like, the whole thing was, and the whole, point was, they were like, Josh, that's going to be difficult to do On the UI toolkit side right now, we just like it's harder. So it was like, let's just use React. So essentially what we've done is, and there's plenty of React, there's lots of open source React kind of drivers for Unity, where you can actually use full React in Unity side of things. So we've been using that along with the component libraries that we've already developed, and for different stuff to make that UI quite reactive on that side. It runs really fast too, which is super important. But from a pure Unity stack perspective, I would say that UI Toolkit's a great option, especially if you have, experience utilizing, kind of web technologies as well, because the way the XCSS or whatever they call it's implemented, you can actually get some good customizations there. And, if you're a Unity veteran and you've been around the block a while, then InGUI might be a better option, because you've probably learned all the hacks there to be able to, get around some of the nuances there that InGUI has, that might necessarily be as, easy to fit on the other side of things. One other element that's actually super relevant on the UI side of things is particle systems and animations. So one thing that you can do, and we have done across all of the 3 implementations I talked about, was we actually built like a particle rendering system for the UI. So you can actually render straight Unity particles, or those VFX particles I was talking about in the runtime, which is super cool. So that means, and what does that mean then? So for example, when you get, like, when you're in the spaceship and you get hit, you can see like this dynamic, like, shield kind of visual effect comes on screen, all that stuff. And yeah, so it's that's kind of what I would recommend on that side. What advice would I give?
So, yeah, what advice? I have some questions as well, because I'm very curious during the whole presentation. So I put that one. What advice would you give to developers that are just starting with Unity and web optimization? What are the things, like, the biggest wins?
Yeah.
Right.
So I like to run the gauntlet, and when I say run the gauntlet, you generally want to make. So here's what I always say to people: create your favorite games. Don't say you want to make World of Warcraft in the browser. That's a bad idea. There'll be danger in those waters, and you'll just spin your wheels. Simple, casual games. Build them. Build 10 of them. Fail fast, fail forward. Make all the learnings. Make the mistakes of not packing your textures into an atlas and then realizing, oh no, my game's like 400 megabytes. What am I going to do? And then when you're going through that process of re-UVing everything and putting it into an atlas, you'll generally never make that mistake again. That's what I would say, and don't be afraid to experiment. I mean, honestly, like, Project Prismatic came out of pure experimentation. I was sitting in GDC and talking to another executive in the industry, and they were like, oh Josh, what's your thoughts on web games, where it's at right now? And I was like, yeah, it's like, it's great. I mean, we publish some games in it. And they were like, yeah, but how far can you really push it? And it was that question of how far can you go that drove us to start making Prismatic. It was literally pure experimentation. So Unity Learn's a great resource. On the crazy game side, the documentation super strong. Like 90% of the learnings you can get from making web games is in the crazy games documentation. Like, it just is. It's just straight there. You don't have to go through the gauntlet to get it. Just read it. I know devs don't like reading documentation. I get it, but those 20 minutes will be 20 minutes well worth it. I can promise you. So do that, experiment, upload your games, learn fast, fail forward, and, just be excited to make new things and, play with all these new features. Don't be afraid to use VFX Graph if you haven't learned to use it before. Don't be afraid to, do all these things. You might fail or it might work. And, oftentimes for every 10 failures, you'll have 1 success. And, that success will make every failure worthwhile.
Another question from Raphael. Are there any common mistakes that you see developer making? Like, that's, you mentioned some about the textures and things like this.
Yeah. The biggest one are downloading stuff off the asset store and thinking it's just going to be ready out of the box to just hit publish. Doesn't work. texture. So a lot of stuff, and textures is the big one. The big one with web games is there's two big issues. Performance is, middling in issue, but generally that's a symptom of a bunch of other mistakes that have happened. A lot of times people make a game for the web, they have it looking great and everything, and then they realize it's 400 megabytes. And they're like, it's probably not going to scale. Or even better, they launch it and they haven't kept control of their memory usage, and then it just black screens. And then they're like, okay, what's going on here? And then they don't know where to go from there, because they're like, okay, I don't really, because debugging in the web is slightly different. You need different tooling, all that stuff. So I would say that is probably the biggest mistake, is not testing early enough. Test as early as you can, iterate. Even if you've got a cube and a scene, just hit build and run, build and run, build and run, build and run, and do that all day long and slowly iterate. Because then when you add something that, is maybe hasn't been done before, you'll be fine. And the other one thing I always say, and this is something especially for the newer guys, use source control, please. Source control is super important. Use your source control, because if you do make a mistake, you can just roll back. Don't be that guy who's trying to figure out what changes he did.
All right. Excellent. We have still a few more questions. I think if we can answer everything, that would be awesome. Yeah. So the next one's for Nishad. What's the most optimized format for audio file? Is it ACC?
So this is an interesting one, and there's different. So I don't know if you've ever seen it, but there's like a framework or like a spreadsheet for the most optimized texture formats. I'll be honest, most of the textures we're actually using right now, because we're battling against file size quite a bit, we're actually using MP3s a lot. Which the problem with MP3s are, they're compact size, they're supported everywhere, it's great. And the cons are they're using lossy compression, and if you compress them too much, they have artifacts. But they're great for like background music, looping tracks. AAC is, really good as well. And it does have better compression and quality than MP3 at similar bit rates. And the only problem with AAC is that it's not natively supported in Unity. So you need you kind of, there's an extra layer there that you have to go. But again, it's great. And then, from that side, just from the base format, you don't for me on the website, I don't think I'm using WAVs much at all. Like I'm just not. They're too big and beefy. They're like you have WAV for like a couple of gunshots, and then all of a sudden it's 2 megabytes, and you're like, oh my god, how do you handle that? So oftentimes we're using these alternate formats and to get it going. From a decompression setting perspective, I always have a little mantra. If it's short, use decompress on load. Like if it's a short gunshot, use decompress on load. If it's a background music, use compressed in memory. And if it's a massive, long 20-minute symphony that's going on, use streaming. And they're the kind of the general settings you'll have. And then on the compression side of things in Unity, if you have, there's like a slider in the audio settings, you can actually hit that at around like, I think usually around 40 or 50, and most out of 100, and most people actually won't notice that you've compressed the audio, and it will reduce the file size a little bit more. Well, we've had great success on the MP3 side. I think every sound effects in Prismatic is using an MP3. I know that's a hedonist thing to say, but it's the truth. Just purely because of file size. And we found that we can get gains. The savings we have in file size and memory is actually better than the CPU overhead that we're incurring on that side, especially because we're using worker threads for everything else. So we're a GPU bound game, we're not a CPU bound game, so we can do that.
Some valuable tips there. Very cool. We got Ahmed again asking, I think that's a very interesting one. When using addressables in Unity, is it better for performance to load the entire scene or individual prefabs? What do you recommend in terms of optimizing performance? So
this is it. So both have their pros and cons. Let me run through, a couple of them. And the cons, the pro of, let's talk loading an entire scene straight off the bat. And your batch loading things, number one. So it makes it easier. And it reduces the number of synchronous calls that you essentially are doing to the cloud. So it's better load predictability. Instead of having, potentially 10 requests that any of them could fail, you only have one big request that's going out. And number two, it's easier to organize. Like, it's just easier to work when everything's in one address. It's just easier from a development mindset perspective. And when you're trying to unload the thing, it's easier because you're only one thing you're trying to unload. You just unload the scene, kick it off, and you're good. And let's talk cons. Higher memory usage, initial memory usage anyway. When you load in a scene, everything's needed right there, right then. So there's a big wall that it has to climb initially on the memory side. So that can be rather than additive, which kind of, does it slower and can cause less bottlenecks on that side. And the other con for that is the initial load time. It's longer because you're loading a bigger scene. So everything needs to be ready before you go. If you make them small enough, then you can get away with that. It's great for semi-static content or elements in the scene that are bundled together on that front. And then on the individual prefab side, we've got pros. Some of them are fine-grained, you fine-grained control. You only load what you need when you need it. It's great. You only use what you need. The other thing is that, it's good for dynamic content and, where you need different objects to be coming in, where you can't just load them in at once. Like, say, for example, in the scene, it suddenly changes. The whole, atmosphere within the scene changes, or items actually change within the scene. You can actually have different sets of items in different addressables to change your scene from a vast open vista to a bludgeoned war scene. You can do that because, they're all independently kind of bundled into their own things, and shorter initial load times is another big one. And the only big con with this is it's harder, and you need to be much about how you're managing the addressables, because you need to load them, unload them. You need to be intentionally about when you're unloading the sets, all that stuff. So it's more like busy work at runtime to actually, make sure that that's all going. And the other thing you need to be careful of is that you're not making too many asynchronous loading calls of small assets, because that'll just bottleneck down the network side of things, and then nothing will get loaded. So you just need to be, it's a balancing trick. On that side. What I found is, if you're doing those big open worlds like that jungle scene that we seen, I would load individual prefabs better, and then I would go from there. Or if it's that smaller kind of space scene where I have these very succinct bundles between the different levels, I just load them in individually as a unique bundle and go from there. And it depends on the file size too.
Excellent. So we got Nishad again. Is URP a great choice for web game?
Maybe it seems a little bit a little bit succinct to say, but I think it's the only choice right now. I don't really see how you could make HRP viable, and we all know built-ins getting booted eventually. So just build in URP. It'll be much easier for you.
Yeah, it sounds like a good tip. We got Bear Games now asking, amazing tips, Job. Thanks a lot. Any tips on optimizing games that are lean heavily on physics? I think that's the one. That's $1 million one.
Yeah, this is an interesting one. So this comes back to a lot of the new benefits of Unity 6 and the web runtime, having those SIMD operations and all that stuff actually helps. So there's a couple of things you can do. Obviously simplifying your colliders is always a big one. If you've got mass meshes, make sure that you're using very simple colliders, and that it kind of, you're breaking them down into primitives as much as possible, and, reduce the solver iterations as much as you can, so that, the computation for frame there is lower, and see if you can push any of that into compute shaders. See what you can offload, see which areas you can go. If I was presented with a really heavy physics game right now, for example, just thinking in the back of my head, right? I'm trying to simulate a vast ocean scene right now where you have multiple objects, being buoyant and something like that. I'd be going straight for a few things. I would be using I would be using the multi-threading side of things to push a lot of those buoyancy calculations that the player isn't interacting with all the time to the web worker. I'd be calculating that on a different thread. Straight off the bat, remove all that from the main thread. You don't need it. And then if I was trying to get like, nice interactions with the water, I'd be pushing that straight to a compute shader, to simulate that. So then you can get them interactions going. And, even for anything, maybe the player's not interacting with it initially, you could do some indirect rendering or any, all that stuff to get that going. But really what the game is here, what can I remove from the main thread to make that physics simulation more, like to spend my CPU cycles on that simulation on the main thread, so you can go from there. So only do what you need to do. Anything that you can fake it. That's 100%. And oftentimes what you'll find is that you can actually fake a lot. You really can if you're smart about it. Which is, where you can kind of come in. Another thing that I would say is use that thing I was talking about, the script culling API, use that, because then you can actually call simulations that's not in the camera frustum. So then you're not worrying about everything that's behind you doing its all physics simulation and that sort of stuff. Just get rid of it. Pause it, freeze it in that moment in time. It doesn't matter what it's doing, even if it's floating in the air. Who cares? The player doesn't see it. And they're probably not going to notice. Generally, if the player's got a bunch of orcs running towards them, they're going to be focused on those, not worrying about, hey, that your thing didn't move.
Awesome.
So you can do that. So you just kind of need to push for that side. And the other angle is, depending if your game's a 2D game, a 2D physics game, or a 3D physics game, you could technically you could also use a different physics system that's more optimized. Heck, if you got some time over the Christmas, build your own.
All right, I got one last question, and then we're gonna wrap up. And I think that's some tips here as well. Do you have any tips for tool or resources that you recommend for developers? Everybody's working in a tight deadline, right? They need to deliver the project by the end of February, beginning of March. So if you have any resources that you think is valuable for them to check it out, please feel free to share.
Yeah, this is an interesting one. So as someone who's been in AAA most of their game dev career, I've always known what deadlines. It's like, it's like, all right, we've got 2 years of work to do and we've got 6 months to do it. How are we going to figure this out? And it comes back to this. There is no secret to, being able to finish things fast and stuff like that. Here's the truth. The reality of it. Here's where developers get bogged down. It's the 80-20 rule. That's the 80-20 rule the whole time. If it's 80% of the way there, don't spend 80% of your time on the last 20%, because oftentimes it only takes 20% of the time to get to that 80%. So it doesn't matter. It doesn't have to be perfect. It really doesn't. You've got this deadline you need to hit. What's better? Having a really, really shiny water shader and no game come the end of February, or have a game that maybe has a decently looking watershed. At the end of the day, it's an experience. It's a play experience. Players get into it, they will enjoy it. As long as it functions, just do it and come back later.
Excellent. Well, I also think that's the case. For those that we also have the web development for Crazy Games, we have the WebGL optimizer, which can help you as well optimizing your game. So you should check that out as well. But your account manager would actually talk to you about this. With that, we come to an end from our first masterclass. I want to thank you, Josh, very much. It was a very insightful. For everyone, our next masterclass will happen on January 16, and there we're gonna have Christopher Loveridge from ByteBrew. So it will be about game analytics on web games, also a very interesting topic. So we hope to see you there. I wish everyone a fantastic end of the year, happy holidays, eat a lot, don't drink too much, and enjoy, and we'll see each other next year. Thank you, Josh. Thank you, Rabia. Thank you, everyone, for watching.
Thank
you.
Thanks,
Welcome
everyone.
to the post-event celebration of Crazy Web Game Jam 2024. Our very first jam has been an incredible journey, and it's all thanks to you. This year's theme, Everything is a Remix, inspired the participants to blend genres, mechanics, and ideas from all over. The results were nothing short of spectacular. Out of hundreds of incredible submissions, these outstanding games were chosen for our incubation program. These teams have shown exceptional creativity, innovation, and dedication. The Crazy Web Game Jam brought together over 2,000 developers from across the world, from seasoned veterans to first-time jammers. Every participant showcased the incredible power of creativity. We had 317 games submitted, a community brought together. We want to extend our deepest gratitude to our sponsors and partners, including Indie Hero, Crazy Games, Unity, and Photon for making this jam possible. We also want to thank all the mentors and judges who helped us during the jam. But above all, we want to thank you, the jammers. Without your incredible talent and hard work, this jam would not have been possible. The Crazy Web Game Jam 2024 was just the beginning. Stay tuned for more exciting events in the future. Until then, keep creating, keep innovating, and see you next time.